Okay. All right, so we're slowly approaching the end. So now, until now, we've been discussing almost only regression. Okay, so regression, you remember, means essentially that the labels are real variables. Okay, we are trying to predict real outputs. So what we want to do now is instead consider what happens when the labels are discrete. Okay, and so you can typically think about classes or categories. Okay, and this is called classification. Which again, you can be thought as a special case of regression, but there are specific cost functions and methods for classification. Okay. 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 This we said. So essentially, for those that are following the notes here, this is the chapter 4. Okay, so we will, sorry, chapter 7. So we'll discuss logistic regression, okay, which is the paradigm of classification technique. Okay, this is the one of the simplest one, and yet it's very efficient. And actually, it forms the building block of neural networks. So neural networks are just many logistic regressors. So let's say what we're going to study now is a tiny block of a neural network, and it can be thought as a single neuron trying to classify data. Okay, while a neural network is an assembly of such neurons. Okay, so right now we're going to study one. It can be thought as one neuron. Okay. So we studied regression, and in particular, we studied linear model. Okay. So right now, until now, let's say if I define Si, I'm not using Y, and that's for a specific reason. Let me call Sy the output of a linear relationship between your vector of features, okay, the data point, your sample Xi, with the inner product with some vector of parameters, okay, which are the ones that you're trying to learn. And maybe you can have some bias, okay, a constant shift is called a bias. And of course, you can always redefine this vector of parameters by adding a constant at the beginning, okay, and a power 0, an additional constant feature, okay, and you can again rewrite this in a linear way, okay, as a linear relationship like this. Okay. What is the simplest thing you could do to make that real number discrete? Let's say you have two categories. So each label belongs to, let's say, -1, 1. So there is the category -1 and the category +1. Let's say the category -1 could represent the set of images on which you find a dog, okay? While the category, so -1, there would be a dog on the image, and +1, there would be no dog, okay? And maybe you want to design an algorithm able to automatically classify this type of images, okay? So you will give it a huge database of images where each row in this design matrix is an image. You give it the associated class, okay? The label is a class in this case. So -1 or +1, there is a dog or not on the picture. And you want to train your model to output automatically the proper label for new images. let's say we want to consider some kind of linear model, okay? In the sense that we want to keep what we did until now, which is linear relationships between the features like this, okay? And the vector of coefficients selects, like weights, it weighs the different features. What can we do to turn this real number into a discrete number, like in -1, 1?
The body, the real body above something, it's like -1.
Yeah, so the simplest thing you can do is just take the sign, which means if it's above 0, it's +1. If it's below 0, it's -1. Okay. So in this case, the label, the discrete label, which indeed belongs to -1, 1, could be taken as the sign of this linear relationship. Okay. Now I drop. Okay, don't put a tilde, but keep in mind that if you want to add a constant shift, you can always redefine by adding a constant feature. Okay. Transpose theta. Okay. So this is the simplest possible nonlinear model. Okay. Why is it nonlinear? Because you see now that the relationship between the label, the output, and the vector of parameters here is nonlinear. Okay, because here you have a linear operation inside. It's just a standard inner product. But then you apply a nonlinear function, a highly nonlinear function. Okay. The sine is a nonlinear function, right? Okay. And this machine here, this machine learning model, this hypothesis class, if you want, is called Perceptron. Okay. And the Perceptron has been designed in the 60s, okay, as the first model of an artificial neuron. Okay. So how can we see the connection with the neuron? So a very simple model of a biological neuron is something that is connected to other neurons, okay, that you can call the features. Okay, it receives some signals. It sums all these inputs, okay, according to some weight, and the weight could be related to the strength of the connection between the two neurons. Okay, and this strength is the how is it called, this connection between neurons? The synapse, thank you, the synaptic weight. Okay, in this case, the synaptic weight, if you want, are this vector of theta. Okay, and these are the entries of the synaptic weights, the inputs. And here you are doing a weighted sum of these different inputs, and then you are thresholding. Okay, so, or if it's above a certain threshold, in this case 0, the neuron fires, it gives you a +1. If it's below 0, it remains silent, that we model with a -1 in this case. You could take 0 and +1 as output, it changes nothing. As long as you have a binary output, it's the same model. Okay, so it's a baby model of a neuron. Okay, it's the simplest possible mathematical model for a neuron, which is doing a linear operation. It's summing all its inputs according to weighted combination, and then applies a nonlinearity. And in this case, the nonlinearity is just a sine function. Okay. All right. So this Perceptron here is an example of what we call a hard classifier. So this hypothesis class belongs to the set of hard classifiers. Why do we call that hard classifier? Because you see that the label here is not sensitive to the amplitude of its argument. Okay, even if you are above 0 by 10 to the -6 or 10 to the -18 by a very small value, you will still project to 1. Okay, if the input was 10 billion instead, it would give the same label. So you completely lose the information about what is going on inside here. So you project continuous number on just a binary number, so you lose a lot of information. Okay, maybe this is what you want to do, maybe not. Okay, we will do something a bit smarter. Okay, instead of trying to directly output the category, okay, the label -1 or +1, we will do something slightly more rich, which is the introduction of what we call the logistic function and logistic regression. Okay, so hard classifier. Why is it a hard classifier? Because it loses the amplitude information. Okay. So geometrically, what is doing this perceptron? So this vector theta here belongs to Rp. Okay, P is the number of features, as always. And this vector Rp defines a hyperplane. Okay, so let's, it's hard to imagine high dimension, but let's say that we are in 2 dimension. Okay, a hyperplane in 2 dimension is just a line. It's something that divides your space into subspaces. Okay, so in 3 dimension, a hyperplane in this case would be a surface which would divide your volume into 2 volumes, into 2 distinct volumes. Okay, in 4 dimensions, what divides a 4-dimensional space is a 3-dimensional volume. It becomes hard to imagine, but that's life. Okay, so in the simplest setting, okay, just 2 dimension, say in R2, this vector theta defines a hyperplane, which is the set of points. Okay, it's the plane which is orthogonal to the vector theta. Okay, right? And indeed, now if you project a vector x, if you do the inner product with theta, if it's on this side of this hyperplane, which is just a line here, let's say here, x is here, then the inner product between this x and theta, okay, it means the orthogonal projection on theta, it gives a positive number in this case. Okay, therefore you will classify as +1. The associated y, it will give a y. Okay, okay, or if I use the notation of my, this is my estimate according to my model, it would give a +1. Okay, if instead I have a point, let's say, which is there, okay, this is x2, this was x1, okay. Now the projection of x2 onto this vector theta, the orthogonal projection is here. It gives me a negative number. This vector theta is oriented. Okay. Is it clear or not? It's okay. Okay. So here I have a negative number, and therefore, according to my model, the y theta of x2 in this case would be a -1, because my orthogonal projection onto my theta for this point x2 is a negative number. Okay, but you see that if my x2 would be very close to this separating plane, okay, it would not change the label. Or if it would be very far here of the separating plane, nothing changes. Okay, so you see, you completely lose the information of how confident is your model on its decision, on its classification. In the sense that it would be natural to say that if a point is very close to the separating plane here, we should be less confident in the label of this point, right? We are very close to the decision boundary. And the closer you are from the decision boundary, the higher is the uncertainty that you are making the right decision, okay? Because if you were changing by a tiny bit your vector theta, you were tilting a bit your decision boundary. This point that was very close to the boundary would change label, right? While the ones that are very far would not. So what we want to do is to design a model which is able to capture that, which is able to not only tell you what label you should select, plus or minus one, but also that tracks an information about how confident is the model in its decision. Okay? Is it clear? So what we want to do now is not just output the label, but we want to output the probability that the label is +1 or -1. Okay? And if we have a probability of being +1 or -1, it means that we have a measure of confidence in our decision. Because typically, if the probability is, let's say, of being +1 is higher than 1/2, you will select +1 as the label, but you also have a measure of confidence in your decision. Okay, if it's almost 1/2, it means that your point is hard to classify. You are very close to the boundary decision. While if your probability is 0.99999, you are completely certain of your decision according to this model. Okay, so this is logistic. This is what is doing logistic regression. Okay. So to introduce logistic regression, let me first introduce the logistic function. Is it clear, this geometrical picture? You should have that in mind. It's very important. Huh? Yes. What do you want to say? Yes. So what I didn't hear well, sorry. So theta is the vector here. And theta, which is also called the classifier, defines a hyperplane, which is the plane that is orthogonal to theta. It naturally defines this hyperplane. Why? Because all the points that are on one side of this hyperplane have an inner product with theta, which is positive. And the points that are on the other side of this hyperplane have an inner product with theta, which is negative. It's like when you plot, you take the Euclidean space X like this. Why is it 0? All the points here have an X equal to 0. You see this direction X defines an orthogonal hyperplane, which we call Y, such that the point on one side have an X positive and on the other side an X negative, right? If instead you have 2 and 3 instead of -1 and 1, for example. The classifier is this vector theta. It's called this. This is the name of theta. So what you're saying is if the classes, the label are not binary, let's say -1 and 1, but let's say -7 and 5. This is what you're saying. Then it doesn't work anymore. It's what you're mean. Okay. It doesn't matter. You can always map, if you want, if the natural labels are -5 and 7, or even categories like abstract categories like dogs and cats, which are not numbers, you can always map them to -1 and 1. Okay. You can always redefine the class cats and the class, like you associate to the class cats the -1 according to this model, and the class dog becomes the +1. You can always map two classes onto a binary number, a -1 and 1, right? A binary variable. Is it clear? Just redefine the classes as -1 and 1. As long as you have two classes, you can always do that. Okay, when you have more than two classes, at the moment you cannot. We'll do that after. You need to do something a bit more rich, okay? But it will be very close to what we're going to do now. Okay. So calling the classes -1 and 1 is completely generic as long as you have two classes or categories, whatever are the categories, okay? So the logistic function, the definition of the logistic function is sigma s is 1/1 plus exponential minus s, okay? And this is a function that takes as input the reals and that outputs a number between 0 and 1, okay? So why did I choose a function that outputs something between 0 and 1? Because like I told you, we want to design a model that will give us a probability distribution as output, okay? From which we'll make decisions, okay, by selecting the label with the highest probability. But what we want as output now is a probability distribution, okay? So we go back to a regression problem, if you want, okay? But not exactly, you will see. So the shape of this function is like this. Okay. So this type of functions in general, that when you approach -infinity, they converge to 0 or maybe to -1, but to some constant like this. And then it's monotonously increasing until it reaches another plateau, and asymptotically it converges to another constant, okay? These type of functions in general are called sigmoids. So if you hear about a sigmoid, it does not mean a specific function, but it means a function with this kind of shape. So the logistic function is the classical example of a sigmoid function, but the hyperbolic tangent is also a sigmoid, okay? But that goes from -1 to 1, okay? Any function of this with this shape is a sigmoid, okay? But we specifically take the logistic, which is arbitrary, but we like it because the output can be interpreted as a probability distribution. It's a number between 0 and 1, okay? And so in logistic regression, the model that we assume, our hypothesis class, is like this. So we will assume, okay, by assumption, our model is that the probability that the label yi, let's say, is 1, given the parameters of our model, which is a vector of coefficient theta and, of course, an input sample xi will be the logistic function applied to the inner product between our classifier and the sample. Okay. So this is our assumption. This is our model. Okay. Okay. So you see, we assume again, as for the perceptron and as for linear regression, a linear relationship here between the features and our vector of coefficients. Okay. So essentially, what we assume here is that what matters to make a decision is a linear combination of the features. Okay. This is a linear combination of the features. And we plug this linear combination of features inside our logistic function, and it outputs a number between 0 and 1 that we will interpret as a probability. Okay. Okay, so we will train our model, which means we will find the vector of coefficients such that if we are given training data, we want to find a classifier, okay, our vector theta. We want to find a classifier such that it will give a high probability to be 1 for the labels, which are actually 1 in our training data, while it will give a high probability to be -1 for the samples in our training data whose label is a -1. It's clear? Okay. So, of course, by normalization, the probability that the label is -1 is just 1 minus this one. Okay. And you should check that this is also the same as the sigmoid applied to minus this inner product. Okay. So now, if we come back to our graphical representation here in 2 dimensions, okay, this is R2. We will train our model. We will find a good classifier, okay, and let's say it's here. Okay, this is our trained. This is the hyperplane associated with the classifier that we will have trained, okay, that we'll have found. I didn't tell you how to train it at the moment, okay? But let's say we will define a cost function that will allow us to find a good classifier, okay? And let's say we found it, it defines this hyperplane in our p-dimensional space, in this case in R2, okay? Now, you see that if you have a point on one side, let's say here, or let's say here, we look again at the orthogonal projection of our point, let's say x1, our sample, on our classifier. And let's say that this number here, this projection that we get is high. It's a large number. which means what? Which means that our point is far from the boundary, okay, the decision boundary. In this case, not only we will be able to classify it, okay, so let's say this x1 is a new sample, okay, we're trying to predict over new points, okay. Not only we will be able to classify this point as +1, okay, because let's say that we obtain, according to our model, that sigma, we project our point, our new point, let me call it x new or x new. It's a fresh sample, okay, in the test data or in completely new points that you've never used. Let's say this is 0.95, okay. Very naturally, what you will do is that you will select an associated label by taking +1, okay. But at the same time, you know that you are confident in your decision, okay. While if instead the point was very close to the decision boundary here, let's say this one is x new 2, then you project you project your new point onto your classifier. You obtain a probability which would be 0.5002, for example. You will also select, you will classify this point as belonging to the class 1, but at the same time, you know that it's a point which is really close to the boundary decision. So it's hard to classify. You're not so confident in your decision, okay? All right. Because here the orthogonal projection is a small number. Okay. You can what, sorry? No, but you are finishing your sentences very low. Speak a bit more loud. I don't. Yes. Yes, if your confidence is very low, like for this red point here, you can decide to call it like, let's say, undecidable point. If you want, you can create a category, which are the points which are too close to the decision boundary to be classified. Yeah, you can do that if you want. You can decide not to classify it. Okay, you can arbitrarily define, let's say, all the points which have a confidence which is not bigger than 0.6, let's say. Okay, a probability of being in +1 or -1, which is lower than 0.6, let's say. You will not classify them. Okay, you can do that. Yeah. Sorry, what I mean is, for example, if the output of a point, of the projection of a point on the classifier as an amplitude, let's say, which is less, yeah, if the probability, let's say, sorry, again, don't forget that this is the probability of this label to be equal to 1, okay, given your theta and your x. Okay, so if this probability is very close to 0.5, you can decide not to classify it. So maybe you can decide that all the points that have a probability which is between 0.4 and 0.6, okay, you will not classify them, never, okay? If this number was 0.1, then you are again very certain of what the label should be. It should be -1. Is it clear? Boris, is it clear? You look
We are doing dependent classification now.
Yes.
Why use some interval and say if the mark is belong to this interval is not classified?
I'm saying that, yeah. I'm saying that here, okay, all the points that are in a strip around the boundary decision, okay, here all the points that belong to this strip, they would have a probability of being +1 which would be less than 0.6 and at the same time greater than 0.4. Okay, so these are points where you're not very certain that it's a +1 and you're not very certain that it's a -1 either. Because you see that if this number is very low, it means that you are very sure that it's a -1. It means that 1 minus this number is large. So this strip, let's say, of probability between 0.4 and 0.6 defines a boundary region here of all the points that are too close to the boundary decision. And you can decide not to classify those ones. You call them undecidable, for example. It's not clear?
That's technical. Because it's a binary.
So what does you mean? Okay. I let you think about it, but I think what I say should be clear, right? I mean, it's not too. So.
In this case, when it means that when we start to predict constant input, it can happen that that input will not have the output.
No. The output, you will always get an output according to this model. Okay, you can always take a point, whatever point you have, if it has a proper number of features, you take a sample, you project it onto your classifier, and then you apply the sigmoid function. This will always give you a number between 0 and 1.
Yes.
What I'm saying is that if this number is too close from 0.5, which means that you are too close from the boundary decision, you can decide, you as a data scientist, not to classify it or to put it in a different category, which is the points that are hard to classify. That's all I'm saying, right? This was the purpose of our sigmoid function, is to get a measure of confidence in our classification. And what I'm saying is that if the measure of confidence is too low, you can just decide not to classify it rather than making mistakes. Okay? That's all. Okay, so let me give a physics motivation behind the choice of this logistic function. Okay. So remember that the sigma S, sorry, is 1/1 plus exponential minus S. Are you able to guess from where is this form coming from physics? From the Boltzmann distribution, okay? We have an exponential minus something, it should ring a bell, okay? Here it's at the denominator, but we will see that this is nothing, okay? So imagine that you have a system with two possible states, okay? Like an atom which is excited or not, or a neuron which is spiking or not, okay? And it has two energy states, okay? So let's say the level, the state yi being +1, it's a state as energy as energy E1, while the state y equals 0 or -1, sorry, let's keep it as energy E0 or E minus 1 if you want. Okay, this is a two-state system. Okay. Now, if you write the Gibbs-Boltzmann, so if this system is in equilibrium in a thermal bath, okay, the Gibbs-Boltzmann distribution is what? Is the probability of y being 1 will be exponential minus the energy, okay? Let's say the temperature is 1, but you can put a temperature if you want. Let's say beta E1 over the partition function, and the partition function is what? Is the sum over all possible states of the exponential minus beta times the energy. So in this case, there are just two states, so it's very easy. Exponential minus beta E1 plus exponential minus beta E minus 1, okay? And now if I if I divide the numerator and the denominator by exponential minus beta E1, I get 1 over 1 plus exponential minus beta E minus 1 minus E1. Okay, and this is my energy difference between my two states. Okay, always in physics, the energy is arbitrary. Okay, the absolute value of the energy never matters. What matters are differences of energies. Okay, you can always add a constant to an Hamiltonian. This will not change the system you are considering, right? The energy is an arbitrary quantity. What is important are differences of the energies between the states. Okay, and here this is what we see. The only thing that matters is the difference between these two energies. Okay, so this logistic function can just be interpreted as coming from a binary system where we define the energy or the energy difference as a linear relationship between the features. Okay. Okay. So we are defining our energy, okay, as linear combinations of features. Sorry. Yeah, if you want. Okay. It's clear? So in physics term, we have a Hamiltonian linear in the features, and we are studying the statistical mechanics of this system which have two states and an Hamiltonian linear in the features. Okay. Okay. So now that we know what is logistic regression, and so we define the hypothesis class and motivated from a physics perspective, we need in some way to learn it, okay? To find a way to obtain these parameters here, okay? So you could tell me, okay, we know a way you define a cost function, for example, the quadratic cost that we already discussed in linear regression, and then you minimize this thing, okay? You could do that, but I claim that's not the best idea. Actually, it will not lead to very good performances because you see the labels are binary. So it's not very natural to try to minimize a quadratic difference between this. Sorry, anyway, you could not do that. Why couldn't you do that? Because we are trying to learn a model here where the output is a probability. It's a number between 0 and 1. The labels are discrete variables, which are -1 and 1. So you cannot compare these labels and the output of this model, right? You remember when we were talking about regression, we were defining a cost, which was typically a square deviation between the true labels, okay, in the data, and our predictions. Okay, this is what we were doing. We were minimizing this kind of cost function. And this makes sense. Why? Because your model is outputting a number which has the same alphabet as the actual labels you're trying to predict. Okay? While the model that we define now is a model which outputs a probability, a number between 0 and 1. While what we want to predict at the end are binary labels. So we cannot write that. It makes no sense. We have to do something else. Is that clear? You can what? You could use a Kullback-Leibler divergence or something like this, but we will do something simpler, something we already discussed, which is maximum likelihood estimation. Okay, so we are talking about right now a probabilistic model. Our model is trying to predict a probability. Okay, so it's very natural to associate to our probabilistic model a likelihood function. Okay, and once we have a likelihood function, one way to obtain an estimator is doing maximum likelihood. Okay, it's to maximize the likelihood of the data that we measured, that we have access to, according to our model. Okay. So what is the likelihood of our data according to our model here? Okay, so now we want to learning by maximum likelihood estimation. Okay, so what is the likelihood of the data of the labels according to our model in this case? So I'm asking, what is the probability of y1? So let me put all this in a single vector, given the x's, the samples, and the parameters of our model. Okay, so you remember in machine learning, we always assume, in any case, that the samples, okay, are IID, they are independent and identically distributed. Okay, so this, whatever likelihood you are considering is always a product over the likelihoods of each point. Okay. So what is this likelihood according to our model? How can we write that? Binomial? So remember, our model is what? Our model is exactly this likelihood by assumption. We assumed, okay, the model is that the probability that a label is equal to +1 given an input sample and our parameter is a logistic applied to the linear project, the inner product between our classifier and the sample. This is our model, okay? This is the model we chose to do classification, okay? Okay, so from there, what is this? Okay, this is the probability of a label, but a label is not necessarily +1. It can be +1 or -1. So one compact way to write this is like this. So, okay, you could write let me write it in words. If the label that you measured, that you have access to in your data, would be a +1, and instead it would be 1 minus this thing. If your label would be a -1, right? Because by normalization, this is the probability that your label, according to your model, is a -1. Okay? And one way to write that in a compact way, okay? Remember, the y's here are fixed. They are fixed by your training data, right? And the x's as well. So they're just numbers that are fixed. One compact way to write what I just wrote is to write this. Okay, why? It's very simple. You check if in my training data for the point, the sample I, the yi is equal to 1, then this gives me something to the power 0. So it gives me a 1. Okay? While this gives me exactly the probability I want. Okay? Is it clear? In the opposite case, if the yi is equal to 0, this would give me a 1. And this gives me exactly what I want, the probability of being a -1 according to my model, which is exactly 1 minus the logistic. Okay? So each time, so you have a multiplication of all these probabilities, and each time you have a y equal to 1, you multiply by an additional sigmoid, and each time you have a y equal to -1, okay, you are, sorry, here I'm considering that the y's are 0 or 1, so in this case it would be yeah, if I'm here they consider the y's to be 0 and 1, sorry. It's, so here it would be, let's say 1/2, and here -1/2. Yes, now it works. Okay. What I wrote before was for the case where the y's are equal to 0 and 1. Okay, in the course. But actually, then it's simpler if we take y equal to 0 and 1. I'm sorry. So let me just. Okay, let me call now here. I change nothing. I just define the y's I belonging to 0 and 1. Okay. You can always, it's just a mapping. Okay. The ones that were -1s, now you call them 0. Okay. It's just a change of variable. Okay. It's not too confusing. It's okay. Okay, so now here I have a 0. It will be easier to write the gradient after. You could do like this, but it just simplifies things like this. I apologize. Okay. So you are multiplying these probabilities, okay, according to your model. And this is indeed the likelihood of the labels that you have access to, these binary variables 0 and 1, according to your logistic regression model. Okay. It's okay. Yes, yes. If the classes are 0, 3? Ah, 3. If you have 3 classes, then you need to do softmax regression, which is what we'll do after. You can have arbitrary number of classes. You cannot do exactly what I said here. We will do a generalization of what I'm saying now. Okay, but it will be almost the same. Okay. So right now, what I say only applies if you have 2 classes. Okay. You have to say yes or no. Is it? You will see. We will do arbitrary number of classes. It will be almost the same. Okay. Right now we have 2 classes. So we have our likelihood function. Okay. For our binary classification problem, where the classes are belonging to the alphabet 0, 1. Okay. But again, if it would be the classes -1, 1, you just do a change of variable and it works the same. It would just be less practical to write the gradient. Okay, so once we have a likelihood, what is maximum likelihood estimation telling you? That you should select, and it's very natural, the parameters that are maximizing the likelihood of the observed data, the observed labels, according to your model. Okay, so the theta that we will select will be the argmax of the likelihood function associated to that, and actually the log likelihood. Again, remember, taking the log changes nothing. Okay, it's an increasing function. So we take the log of this probability. And concretely, this gives us what with what we wrote here? Okay, so this is our cost function. Okay, the log likelihood here is our cost function. Actually, to call it a cost function is something we want to minimize. So the cost function would be actually minus the log likelihood. So to write it in the form of a cost function, okay, cost is something we want to minimize. So now I take an argmin. I'm just doing the same, and now I'm putting a minus in front of all that. This is just to interpret it as a cost. Okay, something you want to minimize is what we call a cost or an energy. If instead it's something you want to maximize, like we had here, people call that an objective, for example, or a utility function, okay? Or a reward if you are in reinforcement learning, okay? So all that are just the same thing. All right, so do you think that we can write before the name of this cost function here? It is cross entropy. Okay. And the cross entropy is, by definition, the log likelihood according to a logistic model, to a logistic regression model. Okay. Do you think that we can do this operation, this optimization by hand? Can we optimize that directly, like in linear regression? Do you think you could write a closed form solution for this optimization problem? Huh? Yes? Okay, how? You have what?
I say, since we are looking for the maximum value of theta, we can derive a system out according to theta to have
Okay, so you should try, and you will see that it's not so easy. I don't think you will be able. So by closed expression, I mean that, okay, you take, actually this function is something you should check is convex in theta, okay? So the minimum is unique, is well defined. But finding a closed solution is meaning that you take the gradient of this cost function with respect to theta, you equate it to 0, and you can write down theta at equal, and you have, you know, some function of the data. Yes, so due to the logistic function, this is not linear in theta, so you will not be able to do that, okay? You should try, but you will fail, okay? Or if you do, you'll probably get the Fields medal or something like that. So maybe you should try. So even if it's convex, you need an optimizer to do it, okay? And this is gradient descent or stochastic gradient descent, okay? So let's write, let's try anyway, okay? Let's try to obtain not a closed solution, but let's try to compute the gradient, okay? And see what happens. So if I compute the gradient with respect to theta of this cost, okay. Okay, the gradient is linear, so you can put the gradient inside the sum. So I will call sigma I this thing, okay? It means the logistic applied to xi inner product with theta. Okay, and what does it give? It gives sum over I, and here we have a minus yi. Sorry. So the gradient of the log, okay, it's the gradient over the sigma, okay. So what is the gradient of the logistic? Okay. If you call that S, this is a scalar. This is the same as the gradient of S times the derivative of the sigma S over ds. Okay, the chain rule evaluated in S equal xi transpose theta. Okay. And this S here is sorry. The gradient of which term? Of this one? No, I'm just computing this. Sorry. This at the moment. Okay. And yeah, sorry, the second term I didn't. Excuse me. Yes. So here the log of 1 minus, I get a plus. Okay. Gradient of sigma over 1 minus sigma. Okay. And this gives you what? It just gives xi. Okay. And the derivative of sigma with respect to S, this is exercise, you check, it's the sigmoid in S, 1 minus sigmoid in S. All that evaluated in S equal xi transpose sigma. Okay. So what we obtain at the end is sum over I of minus yi. Okay, we have a, so yi is a scalar, huh? Xi here is a vector. Sigmoid I, 1 minus sigmoid I over sigmoid I plus 1 minus yi. Sigmoid I, 1 minus sigmoid I over 1 minus sigmoid I. So we see nice simplifications. Okay. Sorry. Yeah, xi here. Plus 1 minus yi sigma xi transpose theta, all that multiplied by xi. Okay. And I claim that if I didn't do mistakes, we still have further simplifications. And indeed, you have this y times this sigma, and here with a minus sign, and here you have this sigma times this y with a plus sign. Okay. So all that gives you sum. Therefore, we have a minus yi plus sigma. Yeah, and I obtain what we should get. So all that times xi. Okay. And we should equate this to the all zero vector. Okay. So this is the equation that we're trying to solve then by stochastic gradient descent. Okay. This is our gradient of the cost. You remember in the SGD equations, we have a gradient of the cost. This is it. Okay, you remember? I just computed for you the gradient of the cost. Okay. So you see, if you can, why did we do that work? Because then you will not compute this gradient of the cost numerically in the algorithm. You just compute it by hand. It gives this function of theta. Now you just have to plug this function of theta in the stochastic gradient descent equations. And you have a way to optimize and to find the parameters. Okay. Is it clear? So you should try to do this computation by yourself once more. If okay, so let's do an application. I will take. I need 15 minutes. That's perfect. This is what remains. Is there any question before I switch to the computer while I have my notes here? So someone said Maxwell-Boltzmann distribution. It's AMNA, but it's really called the Gibbs-Boltzmann distribution. Okay. Maybe in some books it's called the Maxwell-Boltzmann distribution, but I don't think. In general, it's really the Gibbs-Boltzmann distribution. Okay. No question? It's fine. Yes.
Yeah, it means that the loss error is given by which function?
The loss here, our cost, is the log likelihood is minus the log likelihood.
The general loss, like the general loss in the output.
What do you mean by general?
Like when you use the mean square, you compute like the mean square of the general. Yeah, is it the same?
No, this is not the same. No. So the mean square error we discussed, it's a loss if you interpret it from a probabilistic perspective, from a Bayesian point of view. Minimizing the mean square error means that you are assuming that you have additive Gaussian noise. If you write the likelihood for a model with additive Gaussian noise, okay, the Gaussian likelihood, you have an exponential minus the difference to the square. And if you take the log likelihood, you obtain the mean square cost, right? So here it's different. The log likelihood, the likelihood is not anymore a Gaussian. The likelihood is what I wrote here. It's the likelihood according to a logistic model.
And it makes it normally after this you have to compute
the loss is this, is minus this.
okay. And
Theta, yeah.
Is the loss we are looking for.
No, I think you are confusing.
We have to optimize the value.
Yeah, theta are the parameters. The loss is minus this function. It's this. This is the loss here.
Okay.
This is the cost function, yeah.
It means we compute the loss function. We use the cross entropy to find
the cross entropy is the cost function here. It's okay. It was not clear for the others, or so depending on the model that you are considering and the application, you consider different cost functions or different laws, okay, which is just the same thing. when you assume a quadratic cost function, okay, in a probabilistic perspective, from a probabilistic point of view, what you are assuming is that the noise, you have noise that has been added to your labels, and that this noise is Gaussian distributed. And if you write the likelihood according to this probabilistic model, you will get an exponential form with a square. And then taking the log of this, you get the square that you're trying to minimize. Okay, we spent some time to discuss this. So here I'm just doing the same, but my likelihood is not anymore a Gaussian. My likelihood is this logistic model here. I'm assuming that a point, the probability that a label is +1 is given by this logistic form. Right? This is my assumption. So I'm then writing the likelihood of the whole set of labels according to my model, which is what I do here. And then to define the cost, I take minus the log likelihood. And minimizing the log likelihood is the same as maximizing the probability of the labels that I observed according to my model. I'm finding the parameters theta such that according to my model, which is of this form, the labels are actually the ones that I observed, that I have access to. Is it clear? Okay. So this cross entropy is specific to logistic regression. You would have another application in mind. You would have another cost. Okay. So I will stop sharing and I will share here. Okay. Okay. Okay, this is a very nice application. Okay. So this notebook 6, sorry, I'm speaking French, I'm tired, is about the Ising model. Again, we're physicists, we love studying the Ising model. It's a very generic model. So this part, you don't have it in the notebooks because this is essentially the project that I will ask you. Okay, it will be to code by yourself a logistic regression and stochastic gradient descent and to learn MNIST, okay, some data set. While this part is in the notebooks, but so you could have downloaded it again, but I can send you this version, but it's the same. This one, I didn't change anything. Okay, so we have our Ising model again, now which is on a lattice. Okay, so we have a grid, a two-dimensional grid of spins. Okay, and on each node of this grid, you have a binary variable, you have a spin. Okay, and the Hamiltonian, the energy function of our model is the usual Ising model, where the sum here is over the nearest neighbors on this two-dimensional grid. Okay. And the interaction strength is an arbitrary number. Let's fix it to 1. Okay. we will adopt a boundary condition. Okay, and so before entering the detail, what are we going to do? So for this specific model, there is someone extremely smart, whose name is Lars Onsager, who is a Nobel Prize in physics, who has been able, and he got the Nobel Prize in good part because of this computation, he has been able to show that in this two-dimensional Ising model, when there is no external field, so really for this Hamiltonian which is written there, you have a phase transition at a certain temperature. Okay, so again, we associate a Gibbs-Boltzmann distribution to this model. There is a temperature. And at a temperature which is defined by this equation, okay, so if we fix J to be 1, this is an arbitrary constant, the critical temperature is 2 over log 1 plus square root of 2, which is around 2.26. And this is a phase transition between ordered state and disordered state. Okay, so at temperatures which are higher than this critical temperature, the magnetization of your model, of this Ising model, will typically be 0. Okay, you don't have global alignment of the spins. Okay, so in average, half are up and the other half are down in a disordered way. Okay. Instead, your order parameter, the magnetization, will start to be non-zero below the critical temperature. Okay, so you have order that appear. And it happens exactly at this critical temperature. And when we say exactly, what does it mean? Statistical physics, it means in the thermodynamic limit, in the limit of infinitely large system. Okay, when you have very, very large system, the phase transition is precisely at this temperature. Okay. Of course, for finite size, if you take a finite number of spins, the phase transition is not well defined. It becomes you have a crossover between the disordered and ordered states. Okay. So if you were plotting the magnetization as a function of the temperature, it's not anymore a sharp transition. It's something smooth. You have a crossover like this. Okay. From 0 magnetization at high temperature, you will get something smooth, which will go to, let's say, magnetization equal to 1 at very low temperature. Okay. It's only in the infinite size system, in the thermodynamic limit, that you will get something sharp. So you will see or a discontinuity in the magnetization if you have a first order phase transition, or you will get a continuous behavior, but with a discontinuous derivative, with a cusp for a second order derivative phase transition. Okay. In this case, the transition is second order, which means that in the thermodynamic limit, the magnetization is going to 0 continuously, but it touches 0 with a certain derivative, and then it's equal to 0. So you have a little cusp like this. Okay, the derivative is discontinuous there. Okay. So, but here we will take a finite size Ising model of size 40 by 40. So we have 40 to the square spins. Okay, and we will sample the Gibbs-Boltzmann distribution associated with this Hamiltonian, and we will generate many, many configurations at different temperatures. And we will classify these configurations according to the Onsager criterion, which is that above this, if we sample a configuration above this temperature, we should this configuration should correspond to a disordered state. Okay. While if we sample configurations below this temperature, we will label them as ordered. Okay. Because we know we have a theorem by Onsager that tells us that in the thermodynamic limit, above this temperature, they are indeed disordered and below ordered. Okay. So we have an objective criterion to label them. Okay. But of course, like I said, at finite temperature, you have a crossover. So it's not so clear if you observe configurations to say by eye if they are disordered or not. Okay. So we want to train a logistic regression able to classify these configurations in the sense of ordered versus disordered. We have two states, okay? So by Monte Carlo, okay, we will sample many configurations, like 10 to the 4, 10,000 configurations from this Ising model at different temperatures, okay? That will be 0.25, 0.5, 0.65, etc. until 4. And according to this temperature being below or above 2.26, we associate to each of these configuration a label which is +1 or 0 or equivalently ordered or disordered, okay? All right, and once we have these configurations and labels, we want to train our logistic regression. And the hope is then that if you give new configurations that you sample at some unknown temperature, it can tell you, the model should be able to tell you if you are above or below the phase transition point, okay? And maybe you can even use your model afterwards on another type of Ising model or another Hamiltonian. And maybe you will have learned enough features. There is enough common points between this Ising model on which you trained and the new model on which you want to predict, such that this model will be able to let's say, well enough classify the configurations according to ordered versus disordered. You can use it on another Hamiltonian if you want. Okay. So is the task clear? So the data are 10 to the 4 samples, spin configurations, okay, of our Ising model, and the labels are +1 for disordered and 0 for ordered, okay? Each configuration of spins is a vector of size 40 by 40. So it's a large dimensional vector, okay? All right, so here I'm defining the size of my grid, okay? So we have a 40 by 40 system. This is the interaction strength. So it's -1. -1 means what? So here it's -j, which is equal to -1 actually. So it's like if we are putting a -1 here. So we have a ferromagnetic model. Okay, the constant which is in front is negative, which means that the spins, when the temperature is low, they want to align. That's why you get order. Okay, to reduce the energy here, you see that you want the spins to align. Okay. So here it's really -j equal -1. So here are all the temperatures at which we will draw configurations. So, okay, so we will have 16 different temperatures that go from 0.25 up to 4. And the transition is in the middle at 2.26. So here, because this is very slow to actually run a Monte Carlo algorithm to sample these configurations, this is not an easy task. These people are nice, they did it for us. Okay, so we'll just load here the data. All that is just to load the data from internet. Okay, so I will run everything up. Here I'm loading the data. Okay. And here I'm setting up my classification task. The number of classes is 2. Okay. Here I will take all my data, and here I'm just saying that half of the data will be training data and the other half will be test data. Okay. This is the data that I'm dividing in actually 3 classes. There is the data at low temperature enough, okay, so which we can clearly label as ordered. The samples at high temperature enough are clearly labeled as disordered, while you remember we had this discussion. The data, sorry, which have been sampled at a temperature close to the critical temperature, we don't classify them, okay? Because the transition is not, there is a crossover, it's not sharp at finite size. So it's arbitrary to say if we are very close to the phase transition, it's arbitrary to say if you are on the left or on the right of the transition, because there is no actual transition at finite size. So what we're just saying is that for a certain range of temperature, which is close to the asymptotic phase transition temperature, we label the points as critical, okay? And we will not use these critical points for the training, okay? Okay, so here I'm just setting up, so I'm taking the whole data and this is a function that automatically splits the data into training data and test data, okay? All right, so we have 25,000 training samples, 25,000 test samples, and we have 30,000 samples that are too close to the phase transition temperature to be labeled in a clear, definite way. So we just don't use them for the training. We call them critical samples. Let's visualize. Okay, so here I'm plotting. This is just doing a plot. I'm plotting 3 configurations at different temperatures. Here is a configuration at low temperature. So that should correspond to an ordered state. And indeed, we see that we have large regions of spins that are aligned, okay? And we have a boundary between these regions, okay? So we have order. In the critical region, you see that we have some flat regions, but also many spins that are in the opposite direction, okay? We are close to the phase transition. The system has not really decided here whether it's on the left or on the right of the phase transition, okay? And the last configuration here is a clearly disordered state. It's at high temperature. And we see that statistically, half of the spins are up and the other half are down, okay? Let me plot another set of random configurations chosen randomly in the data. Oops. It's not defined. I didn't load everything. So let me see, it should plot now. This is the issue. What's happening? Sometimes the notebooks they bug like this. You have to restart the kernel to make it work. So let me download again. Mm-hmm. Sorry about that. I don't know what's happening. I tested just like 2 minutes before coming. It was working. Ah, okay. Something happened. Ah, okay, no, it's just very slow because there was no battery anymore. Now okay, let's wait 1 second. Okay, so here is another random selection of states at low temperature, close to the phase transition, and high temperature. Okay, you see that here it's even more ordered. There is a single spin that is in the wrong direction. Okay, so one vector, one image like this that has been vectorized is one xi. It's one sample. Okay, the features here are the values of the spins. Each feature is a binary variable, which is +1 or -1, which are the pixels of these images. Okay, these are the spins values. Okay, and the labels is ordered or disordered, 1 and 0. Okay, so here we're gonna train our model. I'm running it right now because it takes maybe 30 seconds. We're gonna train our model using 2 different optimizers. Okay, so we are trying to minimize the logistic the cross entropy, exactly like we discussed, in 2 ways. One way will be to use stochastic gradient descent that we discussed, and another way is to use a convex optimizer from scikit-learn, which is a machine learning package. Okay, which is not, and I will not discuss it. It's a convex optimizer. You can look at what it does if you are interested, but it's another way to minimize the cross entropy, which is not stochastic. Okay, and which is not as generic. It exploits specificities of the form of the cross entropy to find the minimum, but it's not a generic method. Okay, SGD, you can apply it to any cost function, while the technique here is very specific to cross entropy. So we will compare both. Okay, so I'm fitting in both cases. For example, in SGD here, I'm fitting the model using the training data, and I will track, okay, the accuracy of my model on the test data, which is here. And also I will see what it gives on the critical points on the critical samples that I didn't use for the learning. I will see if it's able to classify it correctly. Okay. Okay, so here it's training. So we see the 2 methods. There is this specific technique I told you, which is called liblin. We see the training accuracy, the test accuracy, and the accuracy on the critical points. And the same for SGD. And it will do that for 30 seconds or a minute. And we will see what it gives. And then I'm done. What did I want to say? So here it's a bit slow. Why? Because you see, I'm looping. I'm looping over what? I'm looping over parameters lambda. What are these lambdas? It's the regularization strength. Because here I didn't mention it, but to the cross entropy or to whatever cost function you want, you can always add a penalty, a regularization, right? You remember I said that. Regularizing is actually completely generic in machine learning. And here we are actually doing so, okay? So we are regularizing our vector of parameters theta by adding a L2 penalty. We are adding a ridge penalty, okay? What we did was ridge regression before. It was a linear model plus L2 penalty. Now we are doing L2 penalty for a logistic regression. So L2 penalty added to the cross entropy, okay? To avoid overfitting. And so I'm training the model and testing it on the test data for many different values of the regularization strength. And we will plot the training error and the test error for all this regularization strength. And we will select the penalization, which gives us the less overfitting. So the smaller difference between training error and test error, and hopefully the best test error. Okay. slow. Is there any question? So that when we have the plots, we discuss it 30 seconds and we're done. You have questions on what we did today? So essentially with what we discussed now, you have all the tools, you have everything you need to classify binary data, okay? So data with two possible classes, okay? And the project I will ask you is to implement SGD by yourself, the logistic regression. So to code all that, okay? To code the cross entropy, load data, code the SGD in order to actually classify some data set like what we are doing now. I want you to do it without calling any packages, okay? To code every single line by yourself, okay? Don't worry, it's not a big deal. I did it myself and it's here, okay? So I have a function for the logistic, I have a class, I have here the gradient of the logistic. So this is the cross entropy, the gradient of the cross entropy. I have something that creates mini batches that will be called by SGD. And here I have the SGD and I have three versions. Or the NAG, so the Nesterov accelerated gradient, which are these three lines, or the plain SGD with momentum. Okay, you see that at each epoch, I'm calling this function which creates a new mini batch, etc., etc. And here I'm just loading data. Okay, I will tell you which data you can use, and I'm testing my solvers, and that's it. Okay. It's 1 day work, half a day work if you know how to code a bit. Okay, it's really not hard, but I think it's really important because if you do machine learning later, you can be sure that you will never do that anymore. You will never in your life anymore code an SGD, a gradient, a mini batch. Now everything is one line in Python. Okay, here I'm doing nothing. You can download notebooks from everywhere. You have packages for everything, which is good because you can fast very quickly. You can implement complicated models. Okay, but at the same time, it's a bit a black box. If you don't understand what is going on inside, you quickly do mistakes. Okay, and you cannot interpret the results. Okay, and you have many free parameters. It becomes quickly a mess. Okay, you don't know what is going on. So coding it once yourself in your life, I think it's important, and I can assure you, you will not do it again anymore. But I think it's a good exercise. Okay, we're almost done. I'm sorry. Yes. No, so it's just that. So there are these samples here. Okay, the ones that are critical, that are near the phase transition, that are hard to classify. So I'm not using them for the training. I'm using only states that are well defined in the sense that they are clearly ordered or clearly disordered. Okay. So I'm only using states that were sampled at low and high temperature, but not at temperature close to phase transition. But then I will test the model that I've learned also on critical points to see if the model is also good for this hard to classify states, okay, just as a test. And we will see that the test error on these states will be lower. Sorry, the test performance will be lower because these states are just harder to classify, and we will observe it. Okay. Is there a question on internet or it's okay? Okay. We'll disconnect this. Sorry, on my computer in my office, which is much more powerful, it was taking 40 seconds. Sorry. It's almost finished. But I think it's also coming from the fact that my battery was low and it's okay. Now it should plot. Okay, so here is what we obtained. So what is the accuracy? Our measure of performance is the fraction of states that have been wrongly classified. So when I'm at 70% here, it means that 70% of the samples in the training or test data are correctly classified according to our logistic regression model. Okay. So the lambda, the x-axis, is the regularization strength, is the L2 penalty that we added to the cross entropy to reduce overfitting. Okay. And we see different curves. So the linear, the curves that are in a solid line, is this convex optimization solver specific to cross entropy that I will not discuss, but it's one way to optimize the cost. While the SGD is in dashed, it's much more generic. Okay. And we see that when the regularization strength is too low, we have a very poor performance. An accuracy of 0.5, it means essentially that half of your guess is random. Your labels are random, right? If you associated labels randomly to a binary variable, half of the time you will have the good answer. So 0.5 is the worst you can do. So you see that SGD here is really poor. Okay. But there is a sweet spot in the regularization strength, in the penalty, which allows to reach actually very good training accuracy and test accuracy. And here, this is the point where you have the lowest overfitting. You see the difference between the two curves is rather low, and at the same time, the test performance is high. Okay. And if you continue to increase the regularization strength, you have again a drop in the performance. So this shows you how important it is always to carefully optimize the hyperparameters, okay? And if now we test our model onto the critical states, okay, we see that it's worse in the region where you select the proper value of the penalization strength. You do better on non-critical states, which are those ones, okay? But still we are doing a pretty good job on the critical states, okay? And it seems actually that even if our performance decrease for the other states, the ordered and disordered ones, when the penalization strength is high, we are still able to properly, let's say, not so badly classify the critical states, which is a priori absolutely non-trivial. There is no reason, you know? So the only way to observe that is to actually do the experiment. Okay. So I will stop here. Sorry, I took 25 minutes more. As usual, I think it's very important for you that you try by yourself. Okay, these notebooks. This is how you will understand what is going on. All right. So next time I think what we're gonna do is that I will explain you what is the project that I want you to solve, and I will be around, answer questions, and you can start thinking about it. Okay, at least write the pseudocode. So and try to structure your code in your mind before then going and code it. Okay. And we will do at the beginning, we will do softmax regression, which is generalize what we did today to multiple classes, but it will be almost exactly the same. Okay. There will be a very slight variation with respect to what we did today. Okay. It will take half an hour and then we discuss the project. Okay. All right, I will stop. So if there are no questions on internet, people, I will. Yes.
Sir, I have a question, but regarding to the last session and where I didn't understand. So
I don't hear you correctly. Can you?
okay, yes, I can talk loudly. I have a question regarding to the last session and the notebook. So my question is that instead of using several initial conditions, it's not better to start from the output of one optimization and then use as the output as an input for
Yeah, you could. So our question is, in SGD, is it a good idea to? So if you optimize once and you find a set of parameters according to SGD, and then you want to change, for example, the optimization, the regularization strength, is it a good idea to restart your SGD but initialized on the solution you found previously? So you can do that. So this is called warm start. Actually, it has a name. It's when you use previously learned parameters to learn on new data or in new conditions. It's called warm starting, but it may be a good idea, but it may not be a good idea at the same time. It depends. If you want to speed up your algorithm, it may be a good idea. But the problem if you do that is you introduce bias, because let's say in the previous run, you found a not so good local minimum with prediction performances that are not so good. If you start from there with high probability, you will get stuck in this local minima or close to it. So by introducing more randomness, by initializing again differently, you are reducing this type of biases.
Does it lead to a lower number of steps?
Yeah, if you want to lower the number of iterations, if you want to speed up your code, you can start from the previously learned parameters. Yes, but it may be dangerous as well.
Thank you.
Yes. All right. Okay. So I see you everyone on Friday, and I send you a mail about the project if some of you who are not in class here want to do the project as well. Okay. See you everyone.
Thank you.
Thank you. See you.
Thank you.